In the previous session, we talked about using statistical approaches to assessing heterogeneity. So we had an example where there was evidence of a great deal of heterogeneity. This is the example we had using some of the data from the Brucellosis project. And recall that we had these measures of heterogeneity. So there's a chi-squared test here. We're going to compare this chi-squared test statistic with 15 degrees of freedom, and we obtain a p-value for that. And this p-value suggested we could reject the null hypothesis, and therefore we'd have to conclude that there was heterogeneity, because the null hypothesis is that there is not heterogeneity. And then we also had this other measure, which is the I-squared. And I haven't told you what the I-squared is, but it is a measure of heterogeneity, and it's expressed as a proportion. And when the heterogeneity is high, for example, above 70, we consider there to be substantial evidence of heterogeneity, which means that we can't calculate a summary effect. Now I'm going to show you an example where there isn't evidence of heterogeneity, and we can calculate a summary effect. This is a different data set, and it relates to a publication that we already have, where we're looking at a vaccine for trichomonas. So in this example, what I have is the same arrangement I had before. This is the interface that we were looking at before. This time I have studies, and you can see instead of being listed as 1 through to 10, I have the author's name and the year, and I'll eventually show you how you can do this. This time I've got animals that are vaccinated and then unvaccinated, and the event is whether the animal became infected or not. So I have several rows of data, and then I have a risk ratio and for each study. Now, because this is a vaccine, I am truly expecting that the effect would be protective. So it would protect against the event. And so you can see these are the data that I'm looking at. Now, in this example, we can do the same thing as we did before, and we can ask ourselves, is there evidence of heterogeneity? And so again, I have the chi-squared, and here's the number for the chi-squared test statistic. Here's the degrees of freedom of that, and here's the p-value. And the p-value is 0.19, which suggests that there's not an enormous amount of evidence to reject the null hypothesis. So we might conclude that there is not enough evidence to reject the idea that there's homogeneity. And then we have the I-squared, and this time it's 26, which is quite low. And so 26 might suggest that there's not much evidence of heterogeneity. So what is I-squared? I-squared is the proportion of the total dispersion. And by dispersion, I mean how much these points are dispersed that's considered excessive compared to what we would have seen just by random chance. Now we can look at the values of I-squared. If I can get that slide up again. And the interpretation of I-squared is not an absolute cutoff, it's a general guide. So you can see that values between 0 and 40% are generally considered to unimportant, but values from 30 to 60 may suggest moderate heterogeneity. So see that there's actually overlap here. So this makes I-squared a little bit hard to interpret, and so we often interpret it combined with the p-value for the chi-squared test. And C from 50 to 90 is thought to be substantial, heterogeneity, and 75 to 100 is thought to be considerable. Now, I know people would like an absolute cutoff, and the reality is that no absolute cutoff exists for I-squareds. They just give you a general guide. But in my example here, I really have no evidence that I should reject the null hypothesis, which says it looks like each of these studies is roughly estimating the same thing, which means that we should be able to calculate a summary effect. And what do we mean by that? What it means is we're going to take the estimate from each study and weight it, and then calculate an average weighted estimate. Now, what are we going to weight it by? Well, what we're going to weight it by is we're going to weight it by how precisely we know the estimate. So let's think about these estimates of the risk ratio. What are the factors that affect how precisely we know this number? Well, there are two factors that affect that. One is the sample size, and the other is how the cells, the events, are distributed around the 4 cells. You'll have to go back and look at your formula for the variance of the risk ratio, but otherwise you can just believe me. So see here, I have an estimate of 5, but I have a huge variation. That means that I don't know this estimate very well. So when I weight this, because I have a large variance or very poor estimate, it's not going to contribute much information. It's not going to be given much weight. Now, the way the weights are calculated is not really important for you, although you're more than welcome to read a paper on how the weights are calculated, but this is not a statistics course in meta-analysis. Instead, it's a course on how to do systematic reviews, and that includes understanding a little bit about meta-analysis. But see, this huge variance means that this study has very little weight. But then you see we have a study here that is being given quite a lot of weight. That's because it's quite a big study and because of the distribution of the events. Now, if every study had a weight that was equal, then we would just add all these up and divide by the number of studies. So it would be an unweighted average. But it's not an unweighted average, it's a weighted average. And studies that are more precise are going to be given more value. So this study here is going to be multiplied by a larger weighting factor, and so it's going to contribute more information to the summary effect. Whereas this study here is going to contribute almost nothing. So what we have down the bottom here is the actual final weighted average. Here it is. So if I were to take 1.67 times 0.04, so 4%, so I times 4% times 1.67 plus 19% times 0.86 plus 8.9% times 0.71. So what I'm doing there is weighting each estimate by its weight, which is a function of its variance. If I were to do all of that, and you could do it by hand, this is the number you'd attain. This is the summary effect measure. It says, after taking into account all the estimates I have and the confidence or the precision I have in those estimates, on average, I expect the effect of this vaccine, the risk ratio, to be 0.8, with a 95% confidence interval of 0.63 to 1.01. This number here is the summary effect measure. And I could only measure or report or make inference about the summary effect measure because when I looked at the heterogeneity, the analysis of heterogeneity said it looks like the studies are estimating the same thing, Therefore, you can combine them all into one summary effect measure. So in the next presentation, I'm going to talk about subgroup analyses.